Good morning. Thank you for coming to my presentation. While I was preparing it, I was thinking about the role of firewalls in security. Firewalls have become so common these days that they've really entered part of pop culture. I know I've never seen a movie where the hero is rushing off to update IDS signatures, but you hear firewalls mentioned all the time. There was even a movie last year named Firewall. The movies never get the details right, but the point is that firewalls have become synonymous with security for many people, ranging from senior citizens checking their email at home to, realistically, most IT staff, and even some security professionals seem to be under the impression that firewalls are some kind of magical black box. Drop them at a perimeter, and suddenly your private network becomes protected from the rest of the world. It's not. And I think most people here have already reached that conclusion, but what I'm going to demonstrate today is how anti-DNS pinning attacks can be used to completely bypass perimeter firewalls using technology that's so ubiquitous, only the most paranoid of organizations are completely immune. Before I get going any further, I want to set some naming conventions. You sometimes hear anti-DNS pinning referred to as DNS rebinding, or even more rarely as quick swap DNS. A quick Google search shows that anti-DNS pinning is the most popular term. However, strictly speaking, DNS rebinding refers to a larger category of attacks, and anti-DNS pinning is one specialized form of it. In my presentation, I'll be covering some other types of DNS rebinding attacks, but the primary focus will be on actual anti-DNS pinning. DNS rebinding and anti-DNS pinning are just two forms of a number of web-based attacks, usually involving JavaScript, that have become popular over the last few years. They haven't received nearly as much attention, though, as some others like cross-site scripting, cross-site request forgeries, techniques that allow for port scanning of internal networks, and many more. I'm not going to cover any of these attacks in my presentation, but I will be referencing them and I will be building on them for some of my demonstration. So if you're not familiar with these attacks, I highly recommend that you stay in this room for the next presentation by Jeremiah Grossman and Robert Hansen, where they will be going over at least some of these. I've seen earlier versions of the presentation. It's very good and will definitely help bring you up to speed on some very real threats. There are 5 things that I will be talking about in my presentation today. First, I'll explain what simple DNS rebinding attacks are and how DNS pinning was the right solution for that. I'll demonstrate how anti-DNS pinning attacks can be used to turn a simple web browser into an HTTP proxy using only JavaScript. Even better, I'll demonstrate how a web browser can be turned into a SOCKS proxy using nothing but JavaScript and simple untrusted Java applets. And then finally, I'll discuss some other DNS rebinding attacks and defensive strategies. I'm not going to go over very many fundamentals in my presentation, but I do want to talk about the same origin policy because it's so key to a lot of web browser security. Netscape introduced the same origin policy along with JavaScript and Navigator 2. Essentially, the policy states that a script from origin A cannot read or modify data from origin B. An origin is defined based on the scheme or protocol, so usually HTTP versus HTTPS, the host name, and the port number. The IP address is not considered because of virtual hosting, and we'll see why that's important for this type of attack in a minute. So if any of those 3 things do change, then the origin is considered to be different, and the scripts are blocked. Now, the same origin policy is a good idea. It's definitely helped browser security and it prevented a lot of attacks over the years. But as you'll see in my presentation and the next, it's also very broken in its current implementation. Cross-site scripting is probably the best known way of bypassing the same origin policy. It does that, of course, by basically injecting references to JavaScript in the targeted host. But without some either rare client-side vulnerabilities, a properly secured website is not going to be vulnerable to cross-site scripting. If the attacker controls a authoritative DNS server for an internet domain, a new type of attack, DNS rebinding, becomes possible. As I alluded to earlier, simple DNS rebinding attacks are pretty much the grandfather of anti-DNS pinning. So you'll see a lot of similarities between this slide and some future ones. DNS rebinding attack works something like this. A victim is convinced to go to a malicious website, probably through cross-site scripting. The first thing the browser does is send a DNS query to the attacker's DNS server. The DNS responds with the IP address of the attacker's web server, and the browser puts that IP address in its cache. The browser then sends a request to the attack web server, which responds with some kind of attack payload. Now, at this point, we're still looking at it from a high level, so the payload could be written in anything. The payload pauses long enough for the TTL, or the lifetime on the DNS record, to expire. then initiates a new request back to the same host name. Because the IP address is no longer in its cache, the browser sends a new query back to the attacker's DNS server, and this time receives the IP address of the victim server, which is usually on a private network, the same one that the victim browser is on. So the browser allows the payload to connect into the victim server. Some attack is launched, and the response is forwarded back to the attacker. Now, this whole time, the protocol didn't change, the host name didn't change, and the port number didn't change, which means that none of this violates the same origin policy. DNS pinning was introduced to prevent that type of attack. Essentially, it forces a browser to take the first IP address that it receives for a host name and pin that in its cache for a period of time so that all subsequent requests to that host name go to the same IP address. In theory, no additional queries to DNS should be possible during that pinning period. The first attack against DNS pinning was documented in 1996. It's actually been around for quite a while by some researchers at Princeton. And it was against the Java virtual machine, not against web browsers. We'll talk about it in more detail later in the presentation. Interestingly, DNS pinning is pretty much a violation of the HTTP standard. In RFC 2616, it clearly states that if an HTTP client performs its own DNS caching, that it must respect the TTL that's returned by the DNS server. Now, if this was implemented, simple DNS rebinding attacks would be trivial to launch against browsers. Ironically, the reason that the authors put this rule in the standard was that they were concerned for security. The thought was that if a web client cached the IP address for too long, during that period, the IP address might be reassigned to another party. And if the client decided to send more data to the IP address, then it would be subject to abuse by the address's new owners. Now, realistically, IP addresses aren't reassigned all that often, so the threat isn't all that great. And anti-DNS pinning or DNS rebinding attacks are a far bigger threat. The first well-documented attack method against web browsers against DNS pinning was in 2003 by Josh Soroff, a developer on the Mozilla team. And it was pretty much ignored for a number of years. He posted it just within the browser developer community until last summer when Amit Klein made a reference to it on a post on the WebAppSec mailing list. The attack looks something like this. The victim browser is convinced to download some kind of attack payload. The attacker waits for the browser to either close or causes it to crash, which I think most of us know is usually trivial, and then waits for the user to reopen the browser again. So far, this is pretty simple, straightforward. The hard part is that somehow the attacker has to get the browser to reload the payload from the local content cache on disk. This isn't a simple thing to do. Josh had suggested that a compromised advertising service could be used for that, which is a good idea, but it still doesn't make the attack easy. So after the payload is reloaded, it initiates a request back to the same host name, and of course, this time the DNS server of the attacker responds with the victim server's IP address. On the one hand, this attack is difficult to defeat using simple methods on the browser, at least using current standards, because the DNS cache has to be released at some point, and when the browser closes is a logical time to do so. Persisting the IP address beyond that would be kind of silly. On the other hand, this is a very easy attack to defeat by simply clearing the content cache when the browser exits, and that's something that a lot of users are already doing. It's also very difficult to get the attack payload to reload, as I mentioned, and even if the attacker manages to do all of this, it is still a very slow attack because every time the attacker wants to contact a new server, the process of loading the payload, crashing the browser, and reloading the payload has to be repeated. But there's some more advanced techniques that are available. Shortly after Amit Klein's post to the WebAppSec mailing list, Martin Johns documented that major browsers, at the time he's referring only to Internet Explorer and Firefox, don't fully implement DNS pinning. What he'd noticed was that if the web server becomes unavailable, that the browser will release its DNS cache and requery the server. Presumably, the logic behind this was to allow for more robust recovery from web server outages. But it allows an attacker to coordinate a firewall rule change simulating a web server outage with a DNS change and launching a DNS rebinding or anti-DNS pinning attack. It looks something like this. Again, this is very similar to a simple DNS rebinding attack. The victim web browser is convinced to go to the malicious site, gets the IP address of the attack server back. This time it's actually pinning it in its cache, sends a request to the attack web server, gets some kind of payload back. But as soon as the payload is retrieved, a firewall rule is set up. The payload will try to reconnect to the same host, but the request will fail because of the firewall. The web browser will drop its pinning and requery the DNS server. And of course, the rest of the attack looks pretty much the same. When I'm demonstrating this technique, there's a few components in my demonstration that merit a little bit more explanation. Like I said, the victim browser is using just standard JavaScript. I'm going to be using Firefox in my demonstration, but similar attacks work against Internet Explorer and most other browsers. There's no plugins required. The victim web server is on the same private network as the victim web browser. The attack server is where most of the fun happens. There's 2 IP addresses. Well, first of all, there's a backend database that allows for communication between the different components on the attack server. The 2 IP addresses, the primary one is used for pretty much supporting roles. So it has the authoritative DNS server for the attacker-controlled internet domain. There's an HTTP proxy that accepts requests from the attacker and forwards them to the victim browser. And then there is a multifunction CGI script that on the primary attack server performs command and control functions. So it accepts, provides a web-based attack console for the attacker to view state. It accepts polls from the victim browser and for new commands and for new requests, then also accepts the response data from a victim browser. And on the secondary IP address, it serves up the iframe content that is basically the attack payload that performs the client-side part of the DNS pinning switch. These different components use a number of communication techniques that are fairly well established for JavaScript malware. On the surface, they seem rather convoluted, but keep in mind that all the communication has to be initiated by the victim browser. It's not accepting any inbound connections. So command and control functions are implemented using polls for new scripts, and I'll go into that in more detail in a minute. Data is sent from the victim browser to the attacker server using image requests or HTML forms, and the victim browser requests data from the victim server using XML HTTP request. So going into more detail on these, remember that the same origin policy, in theory, should prevent JavaScript from reading data from any site that is not its origin. A glaring exception to this is other JavaScript files. So the technique that my tool uses and a lot of other JavaScript attack tools is essentially intentional cross-site scripting. A new script tag is appended to the body of the document. The source of the script tag is set to the controller script, that multifunction CGI script that I mentioned earlier. And the query string on the URL is indicating that it's a poll for new commands. The response comes back in the form of a predictably named variable. In this case, it's just an element of an array. Now, in theory, anti-cross-site scripting filters could break something like this, because that's really what it is. I want to make it clear that nothing in my presentation requires cross-site scripting. It's the most elegant solution for some challenges like this, and also for tricking the browser into going to a malicious site, but it's not required. There's a couple of alternatives that I've personally experimented with to tunneling data from another domain involving encoding data into the dimensions, the width and the height of an image, and also into cascading style sheets. These techniques are much harder to detect and don't look as suspicious. I don't really have time to go into them in my presentation, but they are described in the white paper that's associated with the presentation. When the victim browser needs to send data back to the attack server, there's 2 methods. If it's a small amount of text data, that can simply be sent in an image request. The payload on the browser creates a new image object, sets the source to the controller script on the attack server, and the data is just sent in the URL query string. And once the image is appended to the document body, the browser will automatically process it, and the attack server doesn't even have to send an actual image as a response. If it's a larger amount of data that won't fit into a URL, or if the data is binary and the attacker doesn't want to encode it for some reason, then it can be sent using an HTML form. Excuse me. The data is put into an input text box. The action is set to the controller script on the attack server, of course. The method is post. And the target is set to an unused iframe so that when the form is submitted, it won't redirect the web page to to the action. XML HTTP request is an object in the HTML document object model. It pretty much allows JavaScript to create its own arbitrary HTTP requests, usually either GETs or POST. It's best known for being the key component in AJAX sites like Google Maps or Yahoo Mail. Normally, it can only transfer text data because, as the name implies, it was designed for XML content. Thank you to Marcus Granado for documenting how binary data can be transferred by changing the character set to X user defined. I have no idea how he figured this out. Unicode seems to be a rather esoteric implementation of Unicode or use of it. But without that technique, it wouldn't be possible for the attack tool to retrieve binary files like images or PDFs and whatnot. One more other thing real quick. It's important to remember that XML HTTP requests can only be used to contact the origin server. Otherwise, it would be a huge violation of the same origin policy. Because of that, or rather I should say, once the DNS pinning switch has occurred, the victim server is considered origin by the browser, which means that XML HTTP request cannot be used for communicating back to the attack server. And that's why those earlier methods are required for the command and control functions. This is a representation of the demonstration environment. It's fairly typical for a corporate network. The internal network uses private IP space. There's a firewall separating it from the internet. No inbound connections are allowed from the internet. The only outbound connections are on web ports for all hosts and on DNS for the resolving DNS server. There is a Linux server that's running a simple web application with a MySQL backend. There's a Windows server that is running file sharing and also acts as the resolving DNS server internally. And then finally, there's a victim workstation, which is running Windows XP, is fully patched, at least as of a couple of weeks ago it was, with a fully patched version of Firefox. And the user is running with non-administrative rights. So just to emphasize, this isn't using any patchable vulnerabilities. This is just standard browser behavior. On the internet side, there's a fictional popular website that has been infected with cross-site scripting by the attacker. As I'm sure Jeremiah and Robert will mention in their presentation, these are a dime a dozen. Google, Yahoo, all the big names have had problems with cross-site scripting at some point. The attack server, we already talked about those components, and of course there's the attacker's workstation. From a physical point of view, it's implemented on 2 laptops connected by a firewall running DDWRT. Each laptop has multiple virtual machines. Thank you to my colleague Eric Dupre, who gave me some assistance in setting up the firewall and some of the VMs. So I know I've already gone over anti-DNS pinning from a higher level, maybe even a medium level, but I want to go over it again in more detail. It's a fairly complicated attack for web technologies, at least, so I think there's some benefit in this. Of course, it starts off with the victim browser going to a site infected with cross-site scripting and downloading a small piece of malicious JavaScript as a result. The JavaScript will cause the victim to load a new page from the attack web server. Now, in a real scenario, this would probably be in perhaps a pop-under window that's small or an invisible iframe. There are a number of techniques for hiding the new page from the user. In my presentation, I'll be showing it in a large window so that debug statements can help narrate the attack flow. Jeremiah and Robert might be going over some of the techniques for hiding content in their presentation. The base attack page is pretty simple. There's a JavaScript that, using set timeout, causes a new script tag to be appended to the document every second and a half. And as I mentioned earlier, it just points at the controller script asking for a new command. On the first time that a browser polls the attack server, the controller script will insert a record of the session into the database so that the session appears on the attack console. Every poll causes the controller script to look for new commands in the database for the victim browser. Anything that it finds is sent back to the victim browser in JavaScript statements. Now, at this point, the attacker can start probing the victim's network using a number of different techniques. Port scanning, perhaps doing some keystroke logging from the victim. We're going to skip this stage. We're going to assume that the attacker has already performed reconnaissance and has identified the Linux server as a website that he's interested in. So the attacker starts up an HTTP proxy service on the attack server. And when the attacker's browser sends a request to the proxy server, it checks to see if it has seen any other requests from going to that same IP address and same port number. If it hasn't, then it knows that it needs to start up the foundation for a new anti-DNS pinning attack. The first thing it does is create a random host name and DNS record that points at the attack web server's secondary IP address. Actually, let me stop here for a second. Something I forgot to mention. The reason it's important that there's a secondary IP address is that when the firewall rule is set up to simulate a web server outage, it's important that command and control functions still be available through the primary IP address. At the same time, the proxy server creates a command that tells the victim browser to create a new iframe and point that iframe at the controller script on the random host name. And the query basically says, give me a new attack payload for anti-DNS pinning. Once the payload completes loading in the iframe, it sends a message back using an image request to the attack server saying, okay, I'm ready. The payload's done. You can set up the firewall rule. So the controller script creates a firewall rule to simulate the web server outage and changes the DNS record as well. At the same time, the payload on the victim browser retrieves the next URL that it's supposed to be processing and creates an XML HTTP request object associated with that payload. So the web browser will start to process that object and will fail because of the firewall rule. Now, this is not entirely accurate, but it's a bit of an oversimplification, and in my presentation I'm not going to go into the details why, but if you want to know, email me and I can explain it. Essentially, once the pinning expires in the browser, it will dump its cache and requery the DNS server. This time, of course, the DNS server will respond with the IP address of the victim host. The iframe, as soon as this happens, the iframe payload sends a message back to the attack server saying, okay, we're done. I have the victim's IP address pinned in my cache. You can drop the firewall rule, and we're going to proceed with the attack. The browser processes the XML HTTP request, and this time it will connect to the targeted web server, since that's what's pinned in the cache, and get a response, forward it back to the attack server. The controller script inserts the response into the database. The whole time, the proxy server has been polling the database, looking for the response to that original request that the attacker sent. As soon as it sees it, it returns it to the attacker's browser, and of course it's displayed. So I'm sure that is clear as mud. Let's get started with the demonstration, the first demonstration. All right, this is the attacker's workstation, and this is the victim's workstation. We'll start off by having the victim go to a fictional website, already been attacked. This looks like an interesting link. User clicks on it, and has been redirected to a malicious website. Now, of course, as I mentioned earlier, this would be invisible to the user in a normal scenario. If we switch back to the attacker's browser, we can refresh the console and see that it has identified the session. We can run arbitrary JavaScript at this point, which will appear on the victim side. And clear that out. There we go. So at this point, we can start up the HTTP proxy service and confirm that the browser is configured to use it. That's the primary IP address on the attack server. And we can browse to the IP address of the previously identified web server. If we go back to the victim browser, you see that a new iframe has been created. This is the random host name. This is for just HTTP. Now at this point, the DNS record has already been changed and the firewall rule has already been created. It's pausing for a bit, waiting for the pinning to time out in Firefox. While we're waiting for that, I can show you a little bit more detail on the polling. This is the victim browser polling for new commands. Most of these are going to be empty, but this one should contain some data. Basically, a command telling the browser to create a new iframe, pointed at the random host name, the controller script, and asking for a new payload for the anti-DNS pinning. The browser should be pretty close to switching over. Let's see here. Well, should be. We'll wait just a few more minutes, a few seconds. Well, that's not good. It's usually a lot faster than this. Now, you'll notice that Firefox is hanging while it's timing out. That has to do with being aggressive at reconnecting to the victim web server. It's possible to make it a little slower so that the browser is not hung and the user doesn't notice anything. All right, it's getting resets back. Here we go. Okay, good. So this is the iframe that's being used to post back data to the attack server. Here's the content that is being posted. It's basically just a URL encoding of a HTTP response. Switching back to the attack server, we see that, or the attack workstation, it's found a fairly primitive web application that the attacker can start interacting with and get some data back from. Attacker can start looking to see if it's vulnerable to common website vulnerabilities. Which it is, not surprising. And given the quality of it, I'm sure it's vulnerable to SQL injection, which we can test with a quick tautology, and it is. So looking back at the victim browser, you can see the requests as they were coming through different URLs. So at this point, the attacker could continue looking at this application, or probably go on and look for something more useful. Now, there's something that I didn't mention that if you're paying close attention, better switch back. You may have noticed. Because XML HTTP request can only connect to the origin server, and because the origin server has to be in an attacker-controlled domain for the switch to work, when XML HTTP request contacts the victim server, it's going to be seeing a host name and a domain name that's completely alien, which means that for most web servers, only the default website will be responding to these requests. This has led some people to suggest that host headers, validating host headers, might be an adequate form of defense against anti-DNS pinning attacks. Let me be very specific. Host headers are not security. There have been several vulnerabilities in the past with both Internet Explorer and Firefox that allow an attacker to arbitrarily set the host header for new requests. Now, these bugs have been patched, but there's no reason to believe that all browsers have installed those patches, or that similar vulnerabilities won't be found in the future. And in fact, there is a similar vulnerability in Flash. But there's plenty of default websites that are on the internet, and there's even more that are on internal networks. Even if the attacker is unable to find a default website, you still could use a method such as a buffer overflow attack against the web server. Something complicated like chunked encoding is not possible with XML HTTP request, but something with a overflow from the URL or in a header that JavaScript is allowed to manipulate could be launched regardless of the default website state. More likely, though, the attacker would browse the network, look for a long-forgotten, rarely used web application that I'm sure all of us have back at work. It's probably written by junior developers, riddled with SQL injection flaws. And if the attacker is lucky, the backend database will have a tertiary vulnerability, such as XP Command Shell, that could allow the attacker to set up a more traditional and flexible tunneling method. However, if Java is enabled on the browser, then more sophisticated attacks become possible. Before I go into much detail on that, let's do a quick refresher on Java security. There's two kinds of applets, a trusted and untrusted. A trusted applet is either digitally signed, much how ActiveX controls are, or it's installed locally. The trusted applets have pretty much the same level of privilege that the user does. They can access the file system, read, write, create, delete, the whole thing. They can create and terminate processes, and they can have unlimited network access, either outbound sockets to any server or even acting as with a listening socket. Everything else is considered to be untrusted. Untrusted applets have no access to the local file system. They have no process management capabilities. And the only socket abilities that they have are outbound to the origin server, but they can connect to any port on the origin server. Now, the JVM performs its own DNS pinning, and as a result is not going to be vulnerable to the same attacks that we were launching against the web browser. As I mentioned at the beginning of the presentation, the first anti-DNS pinning attack was documented in '96 against the JVM. And what the researchers noticed at Princeton was that if DNS returned two different IP addresses for the origin host name, that Java would consider either one of them to be an acceptable destination for outbound sockets for untrusted applets. Sun addressed the problem pretty quickly and said that in the future, the applets would only be allowed to connect to the actual IP address that the applet file, the class or the jar, was downloaded from. Now, I don't have a 10-year-old copy of Sun or of Java, so I can't say exactly how they implemented it at the time, but as you'll see in a little bit, that is not the behavior that the JVM exhibits today. The Princeton attack, again, was very similar to a general DNS rebinding attack. Browsers convinced to go to a malicious website. The browser could be performing perfect DNS pinning, keeping it in its cache. The attacked web server responds with HTML that contains a reference to an applet, and that causes the browser to initialize the JVM. One of the first things the JVM does is send its own DNS query back to the DNS server controlled by the attacker. The DNS server responds with two IP addresses, which the JVM pins in its cache. The JVM takes the first one and connects that back to it, which is the attacker server, downloads the applet, and the applet sets up a socket connection to the second IP address, which of course is the victim's server. Because both of those came in the DNS response, the JVM considers it to be acceptable and not a violation of same origin. Now, that attack isn't possible anymore, although some variants are. A more effective attack using a technology called LiveConnect is possible. LiveConnect is essentially a bridge between Java and JavaScript that Netscape introduced. It allows Java applets to interact with the document object model on a page so that it can create new content, change attributes, things like that. And more importantly, it allows JavaScript to instantiate standard classes that are part of the Java distribution, including sockets. It's only supported by Firefox and Opera, not by Internet Explorer. So this next demonstration won't work against IE, but there are some similar attacks that I'll talk about that will work against currently any browser that's using the JVM. Earlier this year, Martin Johns and Kanatoko Anvil documented that if JavaScript creates a Java socket object back to the document's origin host name, that, of course, the JVM is going to immediately query DNS. However, since there's no applet file to download with LiveConnect, this query is for DNS pinning only, which means that the DNS server can respond with whatever IP address it wants, and the JVM will connect to it. So there's a number of advantages with this. There's no delay that's caused by waiting for the DNS pinning to time out. Because we have direct access to sockets, the host header restriction is limited. We can just craft our own HTTP request from scratch. But more importantly, pretty much any text and binary protocol over either TCP or UDP are supported. There's even limited ICMP support. This has huge potential. Telnet, SSH, SSL, SNMP, database server protocols, NIS, CIFS. The vast majority of traffic transmitted on a network can be tunneled through Firefox using this method. My demonstration, the environment is very similar to the first one. A few exceptions. Instead of an HTTP proxy, a SOCKS proxy is used on the attack server. For those of you who aren't familiar with it, SOCKS is a protocol that lets pretty much any TCP or UDP protocol be tunneled through a proxy server. The attacker's workstation has a generic SOCKS client bound to the IP stack so that any request that's sent to a 10-dot address range is redirected to the SOCKS proxy. Again, there's no need for a firewall change. And the reads and writes from the sockets can be handled more or less asynchronously using the kind of pseudo-threading that JavaScript supports with set timeout. So let's get started with this demonstration. And let me clear up the environment from the first one real quick. And this time, I'm not going to be doing the fakenews.com. I think that the point was made pretty well. So it's registering itself again. We can test that traffic is flowing properly by sending arbitrary JavaScript. And the attacker can start the SOCKS proxy. The first traffic that we'll send is just going to be a simple Nessus scan. As you can guess, this is going to be a very targeted scan. While this is a powerful tool, it's not as fast as direct access, and watching Nessus run is not very exciting. One of the things that makes this technique so powerful is that once an attacker has access to the internal network, simple tools can be used. It's not even and internal networks are usually not nearly as well secured as the corporate or internet environment. If we switch over to the victim side, you can see that a new iframe has been created. This time it's for a SOCKS connection, the random host name and the IP address. These are the image placeholders for the data being sent back to the attack server. And very similar setup for data being posted back. You can see it changing. It's basically just an array of byte as more data is being sent. If we go back to the attack side and take a quick look at the packet capture, you can see that it's being identified as SMB traffic, which is fine. I'm not cheating. It starts off with a SOCKS handshake, and Wireshark is smart enough to recognize the protocol that's being tunneled, which is SMB in this case, and it's still going over 1080, which is the default port for SOCKS, and it's still all between the attacker's workstation and the attack server. So the scan should be getting pretty close to being done by now. There we go. As you can see, not surprisingly, the server is not very well maintained by the administrators. And this is just using a few plugins for Nessus. We were able to get some reconnaissance out of it as well. It's running Windows 2003. So at this point, we can launch an attack. And again, this doesn't have to be with anything fancy. Something as easy as Metasploit can be used. And we'll be launching just a simple RPC attack. There we go. The payload that I'll be using is just going to be a simple TCP, simple shell bound to a TCP port. Normally, an attacker would probably be using a reverse shell, which would cause the victim server to basically phone back to the attacker over the internet. But because it takes a little bit longer to set up, so I'm going to be using just a straight shell. It'll be a little bit slower since it has to go over the SOCKS proxy, which is why an attacker probably wouldn't use it, but it's faster for just a short demo. All right, and if we switch back to the victim side, you can see traffic coming in. The first thing that Metasploit does is check to see if there's anything listening on port 4444, which is where the shell is bound. There isn't, so Java basically detects that just by throwing an exception. And let's see, it's going to have to launch again. So traffic's coming through. All right, switch back to the attacker side, and always seems slower during a presentation. Here we go. Have a shell. This is basically with root level access, system level. We can show that by just quickly going into the administrator's directory, desktop, switching back to the victim. I'm going to move over to the victim server. This is just the administrator logged in to his desktop. There we go. Just send something really quick. And there we go. So, system level root access from the internet to a private network all over Firefox. Okay. As I mentioned, this attack only works on Internet Explorer, but I'd be willing to bet that the vast majority of us use Firefox as our primary browser, perhaps maybe not with Java enabled. There are a few other techniques, though, that will work against Internet Explorer. Last month, I documented that 3 of them. The first one's not really a new attack per se. Turns out that the Princeton method is still possible when the victim server, the victim web browser, and the attacker server are all in the same subnet. Now, this isn't an extremely useful technique, but it is revealing about how DNS binding does or doesn't work in Java. The second method is a little more useful. It's also based on the Princeton method. If DNS returns 2 IP addresses, the JVM will perform reverse DNS lookup on both of them. If the results match, if the pointer records both have the same host name, then the JVM will consider both addresses to be acceptable for the origin and allow a connection to continue. Normally, an attacker isn't going to be able to set or control the reverse lookups for a private IP address range, but there are a few scenarios where that might be possible. If the attacker had compromised the authoritative DNS server for that IP address range, or if the attacker had compromised the resolving DNS server for the browser, or if some kind of DNS cache poisoning was possible, then this could be useful. I don't consider this to be a really major flaw in the JVM because it does rely heavily on secondary vulnerabilities that aren't all that common. The third method, though, is a lot more powerful. When the JVM is configured to use an HTTP proxy, it will download the applet file, the jar, the class, through the proxy server, but it will still perform a DNS query for pinning purposes. Now, the JVM has no way of knowing if the IP address it receives for pinning is the same IP address that that the proxy server received for downloading the applet, which means that if an attacker can coordinate the DNS response so that the proxy server receives the IP address of the attack web server and the JVM receives the IP address of the victim server, an attack very much like the Live Connect one becomes possible. Of course, this also requires that DNS resolution of internet domains is possible from an internal network, but that's a fairly common deployment. There's a lot of companies that have proxy servers but still allow DNS resolution. DNS and Java are not the only 2 vectors for launching DNS rebinding attacks. Proxy servers have been suspected to be vulnerable for a while, and last month, David Studdard, aka Portswigger, had documented that 2 of them, popular ones, Microsoft ISA and Squid, are both vulnerable. ISA, Internet Security Acceleration Server, enforces a minimum of 6 minutes for the TTL, basically pins the IP address for 6 minutes, which makes a DNS rebinding attack more challenging, but certainly not impossible. And Squid Cache, in compliance with the RFC, respects the TTLs, but that means that a simple DNS rebinding attack is possible. It's important to note, though, that proxy servers, if they're properly segmented, the risk can be significantly reduced. When a proxy server is used as the victim in an anti-DNS pinning attack, the victim server receives its connection from the proxy, which means that a properly segmented proxy shouldn't be able to connect to internal resources only out to the internet. But realistically, that's not always the case. Some people don't know this, but Adobe Flash actually has support for sockets also. It's a little squirrely the way it implements it, but they're there. Earlier this year, Kanatoko Anvil documented that Flash doesn't perform any DNS pinning, which again means that simple DNS rebinding attacks are possible. Last week, the security lab at Stanford released a paper on DNS rebinding attacks. It's very good. It covers some other more details on these, and I wish that I had that they had released it earlier because I would have been able to include some of the new information in my presentation, but I only read it yesterday, so there was not a whole lot that I could do. But I highly recommend the paper. It was very well done and contains more analytical and quantitative data than has been documented in the past. So what about defense? There's several things that have been proposed. Again, the Stanford paper goes into a lot of detail on this. Some of which I think are their ideas, and they also repeat a number of other proposals that have been made in the past. One of the ideas is Class C pinning, so that if an IP address switches, it's only allowed to change to a closely numbered address. This could certainly have some benefit, but would break things because sometimes DNS might be load balancing across multiple geographic locations. Another idea is not allowing the DNS record to rebind to a private IP address. This is an excellent idea. There are very few cases where it's legitimate for DNS to change from a public IP address to a private IP address. And in the handful of cases where it is, well, the user can suck it up and restart the browser. Sharing pinning information is a great defense. The idea is that the browser, the plugins like Java or Flash and proxy servers will all communicate using one of several different proposed techniques, what IP address they're using to communicate with a server. And if the IP addresses don't match up, then the communication is blocked. Realistically, I suspect that vendors are going to be resistant to implementing this because it will change the behavior of tools, and vendors are oftentimes resistant to change. A related idea involves, defense against the restart attacks involves including the IP address in cached content. Basically, adding IP address to the same origin policy, but only for content that's on the disk cache. Personally, I think that browser security policies are a better way to go in the long run because they're going to address a lot more than just DNS rebinding attacks. Disabling Java might be possible at some organizations, but disabling JavaScript is kind of like driving your car around in first gear. Yeah, it'll get you there, but the internet's not going to be nearly as useful without it. Internet Explorer had a good idea with security zones, but they really haven't taken it as far as they could have. Ideally, an administrator would be able to disable all active content for untrusted sites, allow basic JavaScript for medium, basically anonymous sites, and then for more trusted sites, enable powerful tools like XML HTTP request, Live Connect, and so on. That's supported a bit, but not completely in Internet Explorer today. NoScript can do a tiny bit of that, but very little granularity on Firefox. There's a tool out there called Local Rodeo that Justice Winner and Martin Johns are writing. It's still in beta, basically experimental. It addresses a number of JavaScript security flaws, including anti-DNS pinning. Realistically, though, it's not ready for enterprise deployment, and it's also something that should be integrated into the browser, not provided as a third-party add-on. And that's, no insult intended towards their work at all. Another idea that's been proposed is forcing IP address owners and DNS owners to match, so that if I have an IP address, I have to give permission before a DNS record can point at it. If DNS was being designed from the ground up, I'm sure that would be a significant proposal for the standard. Personally, I think that it's unlikely that's going to be retrofitted into the standard, but it certainly would fix the problem. Security gateways, there's some that can add some benefit. For example, there's tools that will block Java applets based on behavior, so that if a applet is going to connect out to a socket, it will be blocked. Speaking from personal experience, those can be very time-consuming to administer due to false positives and also due to exceptions. It's been a few years since I've worked with them, so I'm sure they've gotten better by now, though. A few years ago, a team at Microsoft came up with a list of 10 immutable laws of security. Number one on the list was, if a bad guy can convince you to run his program on your computer, it's not your computer anymore. And while vendors have gotten a lot better at sandboxing active content within a browser, I think that rule still applies and probably will for quite a while. In the end, it might get safer to run programs from strangers, but it's not going to be completely safe. And there are other techniques to bypass perimeter firewalls, like custom-written Trojans. Good security practices is what will provide a broad protection from different attacks. Things like avoiding internal resolution of internet domains. Might not be popular, but it certainly is secure. At the very least, not allowing internet domains to resolve to private IP space or to public ranges that your organization controls, and of course to local hosts as well. That should never be allowed to happen. Network segmentation, while it can be time-consuming to implement, it can still be very effective. John Doe in the call center doesn't need to SSH into your router. Chances are he might not even need access to the internet or to email. Strong protocols that support strong encryption and strong authentication, like SSL, SSH, IPsec, allow tunneling of other protocols over them. And while it's, again, time-consuming to set up, can make it much more difficult for an attacker to spread through an enterprise environment. And finally, if you have a lot of money, which some security departments are blessed with, some of the better application firewalls can actually go a long way in protecting poorly written websites. I wouldn't tell your developers that because it'll just make them lazier, but there's definitely benefit there. And intrusion prevention, it's not perfect, but it can help. Finally, if I did a poor job and you still don't understand DNS rebinding, take a look at this write-up that Christian put on his blog. It's very good. It keeps it simple. Once you understand DNS rebinding attacks, I highly recommend that you take a look at this paper written by the Stanford guys. It goes into a lot more detail than I was able to fit in my presentation. Talks about some other DNS rebinding attacks, and is very good. That's all I have. If there are any questions, please be gentle. Thank you. And also, actually, if you go to dnsrebinding.net, it will redirect you to the page that hosts this. I probably should have put that up there instead.
Do you ever see these DNS rebinding attacks going on in the real world, or is it more of a theoretical type research thing right now?
Excellent question. I know of only one documented case of DNS rebinding being used, and it was very minor. It was more along the lines of a prank than an actual attack. I have not heard of any of those. Of course, that doesn't mean that it's not happening. Historically, attackers are slow to adopt some of new technologies, new techniques.
I've heard the term anti-anti-anti DNS pinning. Is that something you can explain in finite time?
So anti-anti DNS pinning, the idea was that host validating host headers could stop it. Anti-anti-anti DNS pinning would be changing the host header using something like Flash, or there's a technique that I think it was a Meet Klein documented for XML HTTP requests, and that's been patched since then.
Hi. You mentioned some of the limitations of ActionScript sockets. What are those?
I'm sorry, say that again?
ActionScript sockets, what are the limitations of those?
The session has to, or the transmission from the server has to end in a null character. The content, if I remember correctly, I'm not an ActionScript expert by any means, but I believe that the content has to be in XML format, which means that and it might support HTTP or HTML, but you're not going to be able to interact binary-wise. And then
isn't that just limitation of XML sockets? Because in ActionScript 3, they actually have a regular socket for dealing with binary data.
I can't speak to that authoritatively. There's also some limitations based on policies. A server can provide a policy back to Flash that defines what ports it can connect to. By default, if the server doesn't provide a policy, Flash can only connect to ports above 1024, kind of a throwback to the old Unix days.
Mm-hmm. All right, thank you.
Sure. Thank you.